get started on section 6.1, which discusses antiderivatives and antidifferentiation. So, starting with the chapter 6 introduction, we're in the first section. And the way that I want to introduce it is that we normally have worked through, when it comes to arithmetic and other forms of math, where we learned one mathematical operation, and then we learned another one that undoes it. So a prime example would be the sake of taking the number 7 right here, and let's say I wanted to get to the number 11. But what did I do to do that? I added 4 to get to 11. So in that sense, I used the operation of addition. Well, after you've mastered addition, then people start throwing in the opposite operation, which would be subtraction. So if I'm at 11, how did I get back to 7? I used subtraction, which was minus 4. Right? So addition is the opposite operation of subtraction, and vice versa. Subtraction is the opposite of addition. So because they undo each other. Well, the same thing applies to multiplication and division. Right? So if I have 12 and then I multiply by 3, I get 36. So the operation I did was multiplication. Well, if I'm at 36 and I want to get back to 12, then I get to the division. All right, so 36 divided by 3 is 12, and that's how you get that. So now let's take this to your calculus class. Right? So for a long time, you've learned if given a function and then you take its derivative, hit it with ddx, or f prime of x, you'll find that that answer is 3. So now in chapter 6, we're going to be more focused on, okay, I give you the answer, or I give you the derivative, and now you have to give me the function. And the way that you do that is through what's called integration. So right now, you've learned the derivative takes you from function to the actual rate of change. Now we're going from the rate of change to the actual function. So a function big F is called an antiderivative of little f on an interval I, which could be 0 to infinity, 1 to 9, 10 to 44, whatever, if the derivative of big F is equal to little f for all x and I. What does that mean? What the hell does that mean? Well, let's define that with an example. Let's show that if I give you big F, which is 1/4 x to the 4th, let's show that it is an antiderivative to the little f function of x cubed. Well, ultimately, the definition stated that if you had big F and you took its derivative, you wanted to see if you could get to little f. So we have, let me change that, sorry. Big F of x, f prime of x, is equal to f of x. That's what we have to show, right? So big F prime of x is equal to the derivative of 1/4 x to the 4th. So 1/4 x to the 4th, you take that derivative. We'll do it real quick with the power rule. 1/4 times 4 is 1. Drop the power by 1, and you get x cubed, which is what f of x is, right? Little f. Right? So 1/4 x to the 4th is an actual antiderivative. 1/4 x to the 4th is an antiderivative to x cubed, which is little f of x. So it is an antiderivative. Let's take a look at another example. So I have big F, which is 1/4 x to the 4th plus 63. Let's show that it is an antiderivative to little f of x, which is x cubed. So again, we'll use the idea that f prime of big F is equal to little f. So big prime of f, big prime. So that's the derivative of 1/4 x to the 4th plus 63. So we know that differentiation is linear. That means the sum of the the function, if you add two functions, it's the same as taking the derivative of the two functions, right? Not trying to say it so it's confusing. 1/4 x to the fourth plus the derivative of 63. So you'll notice that this part of the the equation comes back down to x to the third, right? You just take the derivative of that. And we also know that the derivative of any number, which was 63, the derivative of 63 is 0. So I'm not going to write 0, but if you notice, it actually is f of x. So if you take a look at the previous example, I have 1/4 x to the fourth gives me x cubed when I find out that that's an antiderivative. And then the next problem says 1/4 x to the fourth plus 63 is an antiderivative to x cubed. So I have two functions that kind of meet that same little f. So this normally happens because of what's called the mean value theorem. So the mean value theorem, it's this big theorem in calculus. It's not that big. There are bigger ones. States that if two antiderivatives make the same little f, then those two antiderivatives, they only differ by a constant. So looking at the two problems that we just previously did, by taking the derivative of both f, big F, which was just regular 1/4 x to the fourth, and then we took the same derivative of the second function, which was 1/4 x to the fourth plus x cubed, we know that both of those come to x cubed. But if you notice, the difference is that there's an actual number or a constant that's on one of the functions. And that's what the mean value theorem states. So in order for us to get the same little f, the big F's only have a difference in constant. So in terms of this, if I were to graph this one, big F of x is equal to x, 1/4 x to the fourth. That would be started at the origin, and then this one would just be 63 units up on the y-axis. So it's the same function, just moved away. So in general, there are infinitely many antiderivatives. So we could have said the same thing about 1/4 x to the fourth plus 1, 1/4 x to the fourth plus 2, 1/4 x to the fourth plus 3. So we don't want to account for each and every number. Since the numbers go on forever, our antiderivatives go on forever. So we normally just account for all of them by using what's called the plus c, which is an arbitrary number. So in general, there are infinitely many antiderivatives, so your answer must account for all of them. So we normally say big F plus c is the antiderivative of little f, where c is any arbitrary number. So instead of writing what is the antiderivative of f, what is the antiderivative of f, we normally use math notation. So the antiderivative, big F, plus, remember that plus c, that general constant, or that integration constant, it's equal to this symbol right here. Looks like a kind of like a big S, right? That is called the integral of f of x with respect to x. So integral, function, and then your differential, your dx, right? And that tells you that you're kind of on the x-axis and you're working on an interval along the x-axis, right? So it just tells you in what respect or on what axis you're on. And we call this integration. So instead of always asking what's the antiderivative, what's the antiderivative, what's the antiderivative, we use this symbol right here, the integral of f of x with respect to x. The integral of f of x with respect to x. So how do we do integration? How do we do it? So the easiest one, or the easiest rule that we can present, is what's called the power rule. The power rule is based on the notion of you having polynomials, or you have some sort of x value raised or base raised to a power, right? A numerical power. So x to the second, x to the third, x to the fourth, x to the fifth. So to do the power rule, what you're going to do is you're taking a look at the integral of x squared with respect to x. So power rule says you take that x squared and you add a power from the integral. So x squared, right? So I take that number 2 and add 1. So it becomes x to the third. So I know that the number 3 is 3 over 1. So if I take the reciprocal and just flip it so that I have 1/3, I'm going to take that number and put it in front of x. So now the integration of the power rule is 1/3, which is down here, x cubed. 1/3, because 3 over 1, the reciprocal of that is 1/3. 1/3 x to the third plus c. So in general, if you just have the power rule, and this is just the power rule in general, if I have x raised to any power of n, except n is equal to -1, then your big F, or your antiderivative, is going to be 1 over n plus 1 times x to the n plus 1. So I had that 2 to 3, and then take the reciprocal and throw it down in front of x. That's pretty much what we did. And then, of course, my plus c always takes into account for all of the antiderivatives involved. Now, I talked to you concerning the power rule. The only one that doesn't work is when n is equal to -1. But if n is equal to -1, you actually have what's called the logarithm rule. So the integral of x to the -1, which is the same thing as 1 over x with respect to x, that's going to be equal to the antiderivative, which is the natural log of x plus c. All right, so the natural log of the absolute value of x. Make sure the absolute value is always there. Natural log of absolute value of x plus c. So this is another rule. So this is the log rule. So if you have the exponential function, e to the x, well, you learned in differentiation that the derivative of e to the x is equal to itself, e to the x. Well, the same thing applies in integration. If I have the integral of e to the x with respect to x, it's simply the same thing. It's equal to e to the x plus c. And that plus c is the general antiderivative, and it takes into account for all the infinite values of c. So what happens if you just have a number inside the integral? Right? So let's just say I have k as an example. If I just have k, where k is any number, then the antiderivative would be that number times x plus c. So an example would be, if I just have 7 dx, that's equal to just adding an x. Technically, we're really using the power rule, but you don't have to derive that. If you just have a number, add an x with it, and then add a constant. 7x plus c. If you have an integral of 0, so if you have 0 as your function on the inside with respect to x, then you just have the actual value of c, right, where c is any number. Right? So it's just based on it just being a constant function. You achieve a constant function. So just like differentiation, integration is linear, what we call linear. And the two properties that are involved that make it linear is that if you take a function and you multiply it by some number, any number, then that's given you c times f of x, the integral of c times f of x dx. Well, just like the derivative, you could pull out that number and just take the derivative of the actual function. Well, the same thing applies to integration. So if you notice I have c times f of x, it's equal to, you can take that c and throw it on the outside of the integral. C times, this is still multiplication, the actual integration of f with respect to x. Now, the other thing is if you have two functions that are being added together, so if I actually have two functions being added together and I want to integrate them, then what we actually have is the sum of two functions. Right? So the integral of the sum of f of x plus g of x with respect to x, that can easily be done by breaking them up into two integrals. So I have the integral of f with respect to x plus g with respect to x. So if I have two functions being added together, I can break them up and take care of the two integrals on the right, just like I would in differentiation. So let's do an example. An example would be in terms of the property. If I actually have a number times an actual function, then what do I have? I have that first property, c times f of x. So in this case, we start with pulling that 4 out, and now I have 4 times the integral of x with respect to x. Right? So now, let's use that power rule. So 4 times, let's do the power rule. So the power of x is really a 1. It's understood as a 1. So I'm going to add another one to that, and that's going to be x squared. As soon as I have that power, I'm going to take the reciprocal, I'm going to flip it to a fraction and have 1/2. And then I'm going to add my constant. So now let's do some simple math. 4 times 1/2, all right, through cross cancellation, you get 2x squared plus c. So the antiderivative of 4x is 2x squared plus c. So how could you test that you come back to 4x? Just take the derivative. The derivative of 2x squared plus c, if you take the derivative of that, the derivative of 2x squared plus 2x squared, that's going to be 4x. The derivative of c, any number, any constant, is 0. So that's what you're left with, which is what's on the inside right here. So you're good. So you can always check your work in terms of finding your antiderivative. The last one that we'll do, because pretty much I already ran out of time, I have the integral of 3x plus 2 over x with respect to x. So I'm kind of using property 1 and property 2 together, but I'm more focused on property 2 that says that if you have the sum of two functions, it's the same as breaking them up and taking care of separate integrals. Right? So I pulled out the 3 of the first term, and then that's x dx, plus pulled out a 2, because it's 2 over 1. Right? 2 over 1 get 2 over times 1 over x is equal to 2 over x. Right? So that's pretty much what I'm using right there. So I pulled out a 2, and I'm left with 1 over x dx. So now I have 3 times, well, from the previous problem, I already know that x, the integral of x dx is equal to 1/2 x squared. And I'm not going to do the plus c yet, I'll do it all the way at the end. Plus 2 times, well, from 1 over x, that means x is equal to, the n is equal to -1. So that's really x to the -1. Well, as soon as I say -1, we're talking about the log rule, that natural log rule. So it's the natural log of the absolute value of x. And then I'm going to add the c all the way at the end. So just doing your simple math, your antiderivative is 3/2 x squared plus 2 natural log absolute value of x plus c. Alright, so hopefully this will kind of open your mind about integration, or the beginnings of integration, and now we'll start going right into the problems from section 6.1, and then we'll keep going through chapter 6. Finally got to doing this, but yeah, we'll get through chapter 6 pretty quickly, or hopefully pretty quickly, because I gotta get on this video stuff. Alright, so if you have any questions, send it down in the comments below. I'll answer those. Or if you want to hit me up on Messenger, FaceTime, or however way you want to contact me, you can do that. And if you like it, say so. And if you don't, say so. And subscribe if you want to see how we're progressing through